Okay, so welcome to the second half of the sugar seminar with Brendon Rhoades telling us about equivariant cohomology and orbit harmonics.
All right. Thank you very much. That was a really nice discussion over the break. And now we can sort of get into this business of, we've had a couple of examples. What I want to propose to be maybe an orbit harmonics equivariant cohomology phenomenon. So we're going to think about a space X that has an action of a rank K torus, C star to the K, T. And we're going to assume that the cohomology ring of X can be presented somehow as an orbit harmonics quotient. So it's R of Z alpha for some Z alpha and C to the N, depending on a K tuple alpha of distinct complex numbers. And we're going to think about these Z alphas lying inside a family. So we're going to look at Z, which is the Zariski closure, inside C to the n plus k of this disjoint union over alpha and C to the k with distinct coordinates of Z alpha cross alpha. And the reason why I have phenomenon is because of the statement in red. It seems to happen that. And I would love to make this more mathematically precise, that you can get a Borel-style quotient of the equivariant cohomology ring by looking at this polynomial ring in n plus k variables and taking the quotient by I of z, right? And here's a geometric picture, which kind of is very much along the lines of the discussion during the break. So we have c to the n plus k up here and c to the k down here. So c to the k is our alpha parameter space. And if I have a generic point alpha and c to the k, where generic means distinct coordinates, well, I have a corresponding fiber up here. So this is a fiber kind of living inside this variety z. It's z of alpha, the fiber over alpha. And this fiber consists of reduced points. And I'm looking at the orbit harmonics rings corresponding to these loci, and I'm sending this locus of distinct points to the origin in this kind of scheme theoretic limit. So I have this scheme theoretic fiber over the origin, right? So this is somehow what's going on in this kind of orbit harmonics deformation world. And we're comparing this with this geometry world where I have a torus, c to the k, acting on x, or c star to the k acting on x. And we have an associated equivariant cohomology ring, and this equivariant cohomology ring is related to ordinary cohomology by, well, this kind of corresponding geometric idea of what does it mean to take a fiber over a point in algebraic geometry. It means applying a tensor product like this, right? So we tensor over a polynomial ring in k variables with C, where really that C is the C where my variables are acting by zero. So this is kind of corresponding to killing off my variables. So we talked about a couple of varieties, really flag variety, Springer fibers that are quite classical. What about some newer varieties? Can we apply our machine there? So the first variety we'll think about is spanning line configuration. So we'll fix k at most n. And we're going to let x and k be the set of n tuples of lines in c to the k, which, when they work together, span c to the k. So this is a variety I defined with Brendon Rhoades. This is going to be an open subvariety of the n-fold self-product of projective space. So if k is at most n, if I give you n lines in c to the k, you'd be pretty unlucky, right? If they didn't span c to the k, you have more lines than you do dimensions, or at least as many lines as you do dimensions. So this is an open subvariety. It's pretty big. If k is 1, what you get is a point. If k is n, you can think about this variety as gln mod t, which is homotopy equivalent to gln mod b. So you recover the classical flag variety in that case. And with Brendon Rhoades, I showed that you can present the cohomology ring of x and k as the quotient of a polynomial ring in n variables modulo an ideal I in k, generated by, well, two kinds of polynomials, the kth powers of my variables and the top k elementary symmetric polynomials. Okay. And it turns out that this quotient ring is important for other reasons. It arises in the context of delta operators in Macdonald theory. And we can also think about this quotient ring in terms of orbit harmonics. So I am going to let alpha 1 up through alpha k be distinct complex numbers. And I'm going to let z and k alpha be this set of points. So it's the set of points z1 up through zn, where the zi have to be among the alphas, and every alpha I has to appear at least once. So that's kind of impossible to understand as I say it. But here's me trying to do an example, z32. So I have two parameters, alpha 1 and alpha 2. And I have the 6 points in C3, where every coordinate is alpha 1 or alpha 2, and I have to have at least one of each flavor. Okay. So here's my variety x and k again. And if you combine my result with Brenda with some work of mine with Jim Haglund and Mark Shimizono, it turns out that the ordinary cohomology of x and k is the orbit harmonics quotient ring associated to z and k of alpha for any alpha. And now we can play the same game, right? We can let z and k be this kind of infinite locus obtained by putting all of our z and k alpha together. It's sitting inside c to the n plus k, right? So we have an action of a torus of rank k on this set of spanning lines, right? It's just acting in the usual way on c to the k. And along with Raymond and Tomoo, I proved that the torus-equivariant cohomology of x and k can be presented as this orbit harmonics-like quotient. And in fact, we have generators for this ideal, right? And these generators have this nice form. So I believe this last generator is known as a factorial Chou function. So I mentioned earlier on that there are other ways besides quotient rings to think about equivariant cohomology. Kind of the other way that's often used in algebraic combinatorics is a GKM presentation, and this is a very rough sketch of that story. So if you have an action of a torus of rank k on a space x, that action will partition x into torus orbits, and these torus orbits are going to have various dimensions. So for example, the zero-dimensional orbits, if you have a nice continuous action, are going to correspond to the fixed points of your torus. And you always have an inclusion of your set of fixed points into your full space. And that inclusion is going to give you a map on equivariant cohomology rings going in the other direction, right? That looks like this. And if your set of fixed points was finite, as you want it to be in this world, this equivariant cohomology ring for the set of fixed points is just going to be a direct sum of polynomial rings. So if the action of t on x is nice, if it satisfies certain things that I will not be defining called GKM conditions, one of them is that this set of fixed points should be finite, then first off, this map I star is injective. And what that means is that you can realize your equivariant cohomology ring in terms of tuples of polynomials. So that's nice. And secondly, the image of this map I star, so kind of the copy of your equivariant cohomology ring inside this direct sum of polynomial rings, can actually be described in terms of certain spline relation, in terms of certain relations. These are relations that come from the one-dimensional t orbits that are somehow connecting these fixed points. So what does this look like for the classical flag variety? Well, my t fixed points correspond to permutations in Sn, where a permutation W is really the flag WB, this permutation flag. And we have a corresponding map, right, on equivariant cohomology, this injection from our equivariant cohomology ring to a direct sum of, or permutations W and Sn of a copy of the polynomial ring for each permutation. And if you want to understand how this map works in terms of quotient presentations, right? We had this quotient presentation of H star t, which was a polynomial ring, and two in n plus n variables, modulo a certain ideal. And this map I star is sending a t variable to the constant tuple given by that t variable. And what does it do to x variables? Well, it sets x variables equal to t variables. So in the slot corresponding to w for permutation w, xj is getting sent to tw of j. So we have a nice GKM action. And GKM theory says that, well, here's how you can decide whether your favorite tuple of polynomials actually lives in this image. Well, we have these linear conditions. So whenever I have two permutations that differ by a transposition, the corresponding difference of polynomials should be divisible by this linear form, ti minus tj. Now, what about this space of spanning line configuration? So here I have x and k, right? And then we're going to think about x and k as full rank k by n matrices with no zero columns, modulo a torus kind of scaling the columns. So you have these lines in c to the k. You put these lines in a matrix. Because I have lines, I can never have a column of zeros. And this matrix had better be full rank if I'm spanning. And now we can see this torus action just acting on the rows. And well, the first thing we want to think about is what are the torus fixed points? And we have an answer here. The torus fixed points are in one-to-one correspondence with surjective maps from an n-element set to a k-element set. So here I have a torus fixed point. It's a matrix with a unique 1 in every column and at least 1 in each row. And such matrices correspond to surjections like this. So that's looking good. And well, I'm going to get a corresponding map, right, from the equivariant cohomology of x and k to a direct sum of polynomial rings indexed by these surjections. And we can say very explicitly what it is in terms of quotient presentations. It does nothing to the t variables while modifying the x variables according to the surjection indexing the component in question. Now, the sad fact of the matter is, x and k is not a GKM space. It does not satisfy the GKM conditions. It's not compact, for example. But you can show, using orbit harmonics, that the map I star is still injective, right? So you can show this purely using algebra without invoking geometry. And an open problem is, well, given polynomials, p sub f, corresponding to surjective maps f, is there a nice combinatorial criterion for deciding when the corresponding tuple of polynomials lies in the image of I star, right? So can you write down just some nice way of deciding this? We have some necessary conditions, but nothing quite sufficient. And finally, in the last minute or so, let's talk about maybe an even more general variety. So if D is at most K is at most N, now we're going to think about this new variety of inlines in C to the K where they don't necessarily span C to the K, but they span a subspace of this fixed dimension D. We call this variety X and KD. It specializes to the flag variety with Xn and N, and more generally, Xn KK is the spanning line variety. It has a torus action of C to the K, just as before. And it has this very nice fiber bundle structure over a Grassmannian, given by, we'll take the sum of the lines. And I'll kind of close with this theorem, joint with Raymond and Tomoo, that we can present the equivariant cohomology of this X and KD space. So we have these n variables coming from the lines. We have these d variables, which are really kind of churn roots that come from this Grassmannian. And then we have our torus variables It kind of makes sense because we had these y variables coming from a Grassmannian. They were lumped together in subspaces. You want to take SD invariants, right? And then you want to mod out by a certain ideal, where your ideal is generated by these mixed EH relations together with a relation on the x variables like that. Future directions, maybe you want to consider other varieties. Here are a couple of ideas. There's a certain variety of spanning subspace configurations where you don't have lines, you have higher dimensional subspaces. There is also a very interesting set of varieties defined by Griffin, Levinson, and Wu, these delta conjecture Springer fibers, which recently have been used by Maria Gillespie, Eugene Gorski, and Sean Griffin to give a representation theoretic model for the QT delta conjecture. And with that, I would like to thank you all for your attention, and I reiterate my question of what is going on. Thank you very much.
Thank you, Brandon.